Okay guys, so in this video we're going to be talking about dynamic programming, one of the most toughest parts in computer science. So it's something which is always dynamic changing. It has a lot of logic and a lot of mathematical aptitude which you're going to be needing to actually solve these type of problems. So let's go and take a look in actually. So the Floyd-Warshall algorithm is also used for in the pairing of solving the all pairs shortest path problem. So the problem is to find the shortest distances between a pair of vertices, between a pair of vertices in a given edge-weighted directed graph. So let's take a look at the components here. A pair of vertices in an edge-weighted directed graph. So a directed graph is basically when two different vertices, let's call this V1 and V2, are actually directed. So the direction is actually specified, and edge-weighted is basically the weights of the edge is specified. So it's finding the all pair shortest path problem. So the shortest path between vertices from, let's see, V3 and this is V4. So what's the shortest distance between, let's call this 7, 10, 2, and this would be 6. What would the shortest path between V1 to V4 be in this case? It would be obviously be this one. It would be 6. So you can see the shortest path. The Floyd-Warshall algorithm will help us in that. So the first thing is we're going to specify a graph here. So it would be 0. So you see the following graph actually represents a graph here. So let's note that the value of graph ij is 0 if I is equal to j. So the graph ij is infinite if there's no edge from vertex I and j. So for vertices I to j, if there's edge weight, it's 0, else it's infinite. So the output, let's go and take a look at how the output is actually deconstructed. So let's take a look at the algorithm now. So the first, we initialize the solution matrix same as the input graph matrix as the first stuff. Then we update the solution matrix by considering all vertices as intermediate vertices. So what would be intermediate vertices? Suppose we have this. I'm going to provide a simple example. What would be intermediate vertices? This would be the source. This would be the destination. So V2 and V3 would be considered the intermediate vertices. Okay, so you basically get it now. So the idea is to pick one by one, pick all the vertices and update all the shortest paths, which include the picked vertex, as the intermediate vertex in the shortest path. So this is confusing. Let's take a look at it again to make sure you guys understand it. So one by one, we're going to pick up all the vertices. So we have 4 different vertices, and we're going to update all the shortest paths, which include the picked vertex as the intermediate vertex in the shortest path. So when we pick a vertex k as the intermediate vertex, we already have vertices 0, 1, 2 to minus k as intermediate vertices. So for every possible ij and source of destination vertices respectively, there are 2 possible cases here. K is not an intermediate vertex in shortest path ij, so we keep the value of dist ij as it is. So k is an intermediate vertex from ij, and we update the dist ij, dist ik plus dist ij. So let me tell you what this means exactly. So we have v1 here, we got v2, we got v3, we got v4, and this is v5 I guess, and this is v6. We're going to stop it right there. So what would be an intermediate vertices? So we have I, which is 1, we have j, that is k, 4, sorry. So we want to go from v1 to v4. So we would go from, I would say, 2 to 1, this would be 3, 2, okay? So we would start with distance ij, that is 2, plus 2, plus 1, that is total of 1 to 4, that is equal to 5. So we would add each different vertex. Next, we would go from v5 to v6 as well to make sure we check it. And in this case, we have 3 plus 2, this is also 5. So the distance is the same, but why are we not selecting this? Obviously because we haven't reached the source destination, there's no link here. So that's what they're basically saying. So the following is the implementation of the algorithm. So let's take a look. First we have stdio.h, then we got 4 vertices like we talked about, and then we have infinite. So define infinite as a large number of values, so it can be 99999. It doesn't have to be infinity in most cases since we don't have enough memory to actually store that. So we're going to have the print solution. The solution is going to be the distance. So it solves all pairs shortest path problem. So we have void float partial. So this will be our main function. So the distance will be the output matrix, and we'll have the shortest distances between every pair of vertices. So we have the distance VV, I, J, and K. So we initialize the solution matrix as the input graph matrix. Or we can say that the initial values of the shortest distances are based on shortest paths, considering no intermediate vertices. So they're just basically the intermediate or the input graph. So the solutions matrix is basically the input in the first step. Then we use two for loops and actually iterate to each possible vertices. And then we actually calculate the distance. So we actually go and initialize that. So what this means is we're just initializing the solution as the input graph. Okay, so now we add all the vertices one by one to the set of intermediate vertices. So before the start of iteration, we have the shortest distances between all the pairs of vertices, that is the input graph, such that the short distances consider only the vertices in set 0, 1, 2 to k minus 1 as intermediate vertices. So we have to go to k minus 1. We talked about why we should do this, why do we select 4 instead of 5, 6 in the example 1, 2, 3. Why do we do that? Because they were k minus 1. So that's what it's saying. So at the end of the iteration, vertex number k is added to the set of intermediate vertices, and it becomes 0, 1, 2, k. So in this case, what would be the intermediate vertices for 3? It would be 1, 2, where 2 is actually equal to k minus 1. And k would be actually equal to 3. You get it? So I think you now understand what I'm trying to say here. So actually, for every k to vertices, we're going to actually pick the vertex as a source one by one, and we're going to pick all the vertices in the destination. So for j less than the number of vertices, we would say as we picked up each vertices, now we're going to have to go and calculate the distance. So if the distance of ik plus k of j is less than ij, then we update it, else we don't, since we want the minimum. Okay, so we're going to print out the shortest distance, and there it is. So now we have to provide the utility function. So the utility function is actually the area which actually helps us calculate the distance here now. So we have the print solution utility. So we're going to print the following matrix shows the shortest distance between every pair. So if you just want the source and destination, that will be fine, but for every pair, we're going to have to do it differently. So you have two for loops for ij, and then we have all these are infinite. We talk about how these are infinity, and it's 0 for the base case. And then we're going to print this. Also, we're going to just print out the values of dij. In most cases, if dij is given, if the distance is actually given in the input graph, we're going to print out that, or we're going to add infinity. So we're just having the main function here. It's simple as that. This is the basic graph. This is the input graph which I'm talking about. This is the first thing which we're going to be considering as the solution. And then we're going to be using the floated washer graph algorithm to actually go and do that. So the output is actually, we talked about how 0 is being the normal case for the distance, and how infinity is actually occupying all these cases. So this is the shortest base distance. So let me tell you what this actually means. So this is basically, since we have 4 vertices, it's actually 0, 1, 2, and 3. And this is actually 0, 1, 0, 1, 2, and 3. So you can see the distance between 0 and 0 is 0, 1 and 1 is 0, 2 and 2 is 0, 3 and 3 is 0. And 3 and 0, since this is a directed graph, that means 0 to 3 gives us 9, but there's no graph or no pointer going from 3 to 0. That means it's infinite. There's no valid graph. So that's why we mark this as infinity. So you can see what I'm saying here. So the time complexity for the floated washer is huge. Why? Because we have three for loops. We have for I less than v, we got j less than v, we got k less than v. So it's such a headache. We're going to have to do 3 times. So that's the basic time complexity here. The above program only prints the shortest distances. We can modify the solution to print the shortest paths, also by storing the predecessor information in the separate 2D matrix. So this is going to be quite complicated. Maybe we can do that in another lecture, I guess. So also the infinite value can be taken as int max with limits from h. So that's why we have the limits from 2 power 32 minus 1 or 2 power 31 minus 1 in this case. So this is the basic collection. We don't want it to go to an overflow, so that we don't want to take it literally as infinity. So you can actually see how this is actually modified. This is the basic algorithm which you should remember for this case. So we have defined, we got limits, This is the base case. If ik is not equal infinite and kj is not equal infinite, then if this is less, we're going to print out this one. This is the main algorithm. So if you remember this point correctly in summary, then you are good to go. There you go, guys. I hope you learned about Florida Washoe algorithm in complete detail. So I'll see you in the next video.